This podcast will cover the concept of continuity and in behavior. Continuity refers to whether the graph is continuous or not. A continuous graph can be drawn without ever picking up a pencil. If a graph has discontinuity, there is a place where there's a break. There are different types of discontinuity. The first type is infinite discontinuity. When you have an infinite discontinuity, there is a vertical asymptote in your graph at some point. It can happen in different ways. In one way, the graph can move close to the asymptote in the same direction from both sides, or it could move in different directions from both sides. Either way, the function has an infinite discontinuity. Another type of discontinuity is point discontinuity. In point discontinuity, there will be a hole. The graph will proceed to the hole, skip over the hole, and then move beyond the hole. It doesn't have to be a linear function with a hole. It could be a rational function, quadratic function, but there will be a hole or point of discontinuity somewhere in the graph. The third type of discontinuity is jump discontinuity. In this, there's also a gap in the graph, but the sides of the graph do not match up. So for example, you might have a function that arrives at a point here, and then it may pick up and continue on from a different place. You can see that there is actually a jump in the graph from the left side to the right side. Continuous graphs have no interruptions. To check for discontinuity, we need to find out where the function would be discontinuous. One place is if the denominator of the fraction is 0. That would be undefined. A second way is to see if there is actually a point that exists at that particular value of x. So what we'll do is we graph it, look at a table of values, try to evaluate the point, and see what's going on. So on our first example, I wanted to determine if 3x squared plus 7 was continuous at x equals 1. So the first thing I do is I check by substituting in 1 into the problem to make sure that there is actually a point there and not a hole. So I did 3 times 1 squared was 3 plus 7 and ended up with a value of 10. That means when x equals 1, there is an ordered pair at 1, 10, so there is a point at that spot. Now we need to check, either graph the function or check on the table to see if the values look like they continuously move through there. We were checking at 1. I looked at 0.8, 0.9, 1, 1.1, and 1.2. And if you look at the values, you can see how they appear to be in order. So it does look like the graph is going to be continuous at x equals 1. If we actually graphed this function, it would have looked like this. It would have been a parabola that had been shifted up 7, and the amplitude was 3, so it was very narrow. So the point did exist at 110. In our second example, we have a rational function, and we need to determine if the function is continuous at x equals 2. So the first thing we're going to do is substitute 2 into the problem. And when we do that, we get 2 minus 2 over 2 squared minus 4. That gives us 0 over 0, and because we cannot divide by 0, it is undefined at this point. The problem is I don't know what type of discontinuity it is, but I can definitely tell that it is discontinuous. Now, if I look at the values near 2, I can actually look at my table of values. When x was 1.7, y was 0.27. When x was 1.8, y was 0.26. When x was 1.9, y was 0.25. When x was 2, there was an error. When x was 2.1, it was 0.24. And when x was 2.2, it was 0.23. If you look at these values, 0.27, 0.26, 0.25, skip 0.24, 0.23. They do look like they're in order, so that means this is more than likely going to be a point discontinuity. Now we're going to look at the same function at x equals negative 2. When we substitute negative 2 in to evaluate for a point, we get negative 2 minus 2 over negative 2 squared minus 4. We end up with negative 4 over 0. Again, it's going to be undefined, which means we have some sort of discontinuity. The question, is it a point discontinuity, or is it an infinite discontinuity or a jump discontinuity? So we're going to look at our table of values again, where x is 2, near negative 2. Notice the numbers I subbed in were negative 2.3, negative 2.2, negative 2.1, negative 2, negative 1.9, negative 1.8, negative 1.7. As we're going towards negative 2 from the left side, my numbers keep getting smaller. Negative 3.3, negative 5, negative 10. So the numbers on this side are decreasing or going down. As we approach negative 2 from the right side, negative 1.7, negative 1.8, negative 1.9, you can see that the numbers or values are increasing, 3.3, 5, and 10. This means that on the left side of negative 2, my numbers are going down, and on the right side of negative 2, my numbers are going up. Therefore, I can tell by looking at those values that I have an asymptote at x equals negative 2. The next thing we need to talk about is how you describe the end behavior of a function by looking at the graph. When we're describing end behavior, we're talking about the behavior as x approaches infinity. In other words, the farther we go to the right, what is happening to the physical graph? So on the right side, I would say as x approaches, and notice I use the arrow to indicate approaches, infinity, what is happening to my y values? Well, as x approaches infinity, my y values, if you look at them, are continuing to go up, so it's also approaching infinity. When I look at the left-hand side, I'm looking at what happens as my x values go to the left. So I'm going to start at the origin and move towards the left. And as x approaches negative infinity, my graph is actually going down. So my end behavior on this one is as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y approaches positive infinity. Let's look at a different function. On this problem, as x approaches infinity, so I'm starting here near the asymptote and going to the right, so as x approaches infinity, what is happening to my y values? Well, my graph looks like this. My y values are getting smaller and smaller and smaller, and they're getting very, very close to the value y equals 0. So I would say y approaches 0. Look what happens on the left side. On the left side of my asymptote, as x approaches negative infinity, in this case, my y values as I go to the left are getting closer to 0. They're on the underneath side of the graph. It doesn't matter. It still means I'm getting close to 0. So I would say as x approaches infinity, y approaches 0. You can also describe behavior near an asymptote. If I were going to do behavior near this asymptote, I can see from my graph that my asymptote is at negative 2. So if I want to describe what's happening to my graph as x approaches negative 2, I have to do it two ways. As x approaches negative 2, and then to indicate the right-hand side, I'm going to put a little positive sign up there to the right, almost like an exponent. And it says as x approaches negative 2, so I'm going towards negative 2. I'm going to use a different color here. I'm going towards -2 from the right-hand side. Where are my y values going? Well, as I'm approaching -2 from the right-hand side, y is approaching infinity. Look what happens as I approach -2 from the left-hand side. And I would write it this way. As x approaches -2, and to indicate the left-hand side, I use just a little negative sign up there like an exponent. What's happening is I come towards the asymptote from the left-hand side. My graph is going down. So I would say y approaches -infinity. The next thing we're going to look at are critical points. And by definition, critical points is where the tangent line to a graph is either vertical or horizontal. We have different types of critical points. We have a maximum point, which is a top of a hill, a minimum point, which is the bottom of a valley, or a point of inflection, which is where the curvature of the graph changes. Now, if you're looking at a graph, an absolute minimum happens at the absolutely lowest point on the graph. An absolute maximum is the absolute highest point on the graph. A relative minimum is at the bottom of a valley, but not necessarily the lowest point on the graph. And a relative maximum is the top of a hill, but not necessarily the highest point on a graph. So, for example, if I had a graph that looks like this, I have a lot of minimums going on here. I don't have any absolute maximums. There are no absolute maximums because the graph continues to go up. It never has a top high point. However, right here, I have a relative min. It's a low point, but it's not the absolute lowest point. I have a relative min here. I have a relative min here. I do have an absolute minimum right here. That is the absolute lowest point that the graph is going to go to. It's never going to go any lower than that. Now, in addition to all these minimums, I also have some maximums. It's just that none of them are absolute maximums. So here, this would be a relative max. This would be a relative max. And this would be a relative max. If my graph were one that just started and stopped, it did not continue on, notice no little arrows at the ends. In this case, I do have an absolute min and an absolute max and a relative max. The point at the beginning is neither a max or a min. It's not a high or a low. This point right here is the top of a hill, but it's not the highest point the graph reaches. So this is a relative max. This point is the highest point the graph reaches, so it's an absolute max. And this point is the lowest point the graph ever reaches, so it is an absolute min. You can do it on your calculator and ask it to do maximums and minimums. The instructions are right here. Finding extrema algebraically. Basically what you're going to do is substitute in the value of the number, then add 0.1 and subtract 0.1 and evaluate that, and determine if the number is the highest value, the lowest value, or if it's just in between. If it's in between, you have a point of inflection. If it's highest, you have a max. If it's lowest, you have a min. In our example, I was using the function x cubed minus 3x, and I was interested in what happened at -1. So I evaluated -0.9, -1, and -1.1. When I did -0.9, I got 1.971. When I did -1, I got 2. When I did -1.1, I got 1.969. This is the point I was interested in. I was interested in -1. So I'm going to compare the 2 to the other two values. Is it higher, lower, or in between? And it's higher than both of those, which means this is going to be a maximum.